Hello, everyone, and thank you for being here today for part 3 of Assessing the Impacts of Fires on Watershed Health training. My name is Sativa Cruz. I'm an applied researcher with the Bay Area Environmental Research Institute at NASA Ames and part of the ARSET Ecological Conservation Team. Today, I'm going to present alongside my colleague, Britnay Beaudry. As an overview, I'd like to take a moment to provide a recap of the learning objectives set forth for the training series. By the end of this training, participants will be able to distinguish, compare, and contrast the biophysical conditions pre and post-fire. You'll be able to analyze the key fire science criteria to select appropriate data from satellites and instruments for a given watershed. You'll acquire land use and land cover maps for a region of interest, select river basin and sub-basin boundaries for a watershed of interest, and recognize how to develop a river basin scale model using SWOT to simulate the quality and quantity of surface and groundwater. The prerequisites for this training are linked here, including the fundamentals of remote sensing, satellite observations and tools for fire risk detection and analysis, using Google Earth Engine for land monitoring applications, and the Texas A&M instructional videos for SWOT. Just a reminder, this is part 3 of this series. Following this training, the homework will be open and it will be posted to our training webpage. Please note the due date of July 27. A certificate of completion will be awarded to those who attend all the live sessions and complete the homework assignments before the due date. Now, on to part 3 of the training series, using Google Earth Engine to monitor post-fire impacts. I'd like to take a quick moment to acknowledge the wonderful ARSET Ecological Conservation Team, Britnay Beaudry, McCullum, and Juan Torres-Pérez. This training would not have been possible without the unwavering support of each of my teammates. Our learning objectives for this training include identifying urban extent and population datasets, acquiring a global land cover map, and datasets useful for assessing the impact of fire on communities, and evaluating the severity of post-fire burns within a watershed of interest. As with the prior trainings in this series, our case study is the 2018 Woolsey fire. This fire burned approximately 100,000 acres. State and national parklands were affected and resulted in closing for months. More than 250,000 people were evacuated due to this fire, and it is estimated that $52 million was dedicated to suppression costs alone. What we learned in part 1 through a pre-fire risk assessment was about fire science criteria for drought conditions in a given watershed pre-fire to select the appropriate data from satellites, instruments for a watershed of interest. We learned how to delineate river basins and subbasins. We also learned how to calculate anomalies in biophysical and meteorological conditions for a watershed of interest. Specifically, we derived the Standardized Precipitation Index, or SPI, to address dry conditions, as well as monitored anomalies of soil moisture and the Normalized Differenced Vegetation Index within a watershed. This all took place in Google Earth Engine, and we notice SPI and NDVI deviations and anomalies for pre-fire. We will be building on this analysis during our presentation. In part 2, we took a closer look at a river basin scale model using the Soil and Water Assessment Tool, or SWOT for short. We identified the physically based model components necessary to run a SWOT model to predict the impact of management on water and sediment in a watershed. We ingested Earth remote sensing data into the SWOT model using NASA Access and discussed best practices used to conduct calibration in SWOT. SWOT can be used to quantitatively constrain fire-related increases in water quantity and water quality parameters. We learned that fires have been shown to increase stream flow sediment and nutrient loads in watersheds. And we were able to observe this for the Woolsey fire, as there were fire-related changes in the first year. Following the fire, there was a lot of precipitation, which resulted in discharge and sediment load peaks. A lot of information was covered in the first two sessions, and we'll continue to build on our understanding of the Woolsey fire for part 3. I want to remind you that you're free to enter questions as we go. We will try to get to all the questions during the Q&A session, and any remaining questions will be answered in the Q&A document that will be posted to the training website about a week after the training. So now on to our first topic, burn severity mapping. Satellites can detect many aspects of fire, including active fire mapping, meaning the fire is still burning during the satellite overpass. Information about an active fire is gathered in 3 ways. 1, being smoke. If there is a fire, there will be smoke visible in the satellite imagery. 2, temperature anomalies or hot spots on the ground. The observed temperature will be elevated where a fire is burning. And the 3rd is light. Most fires produce light while burning, so satellites observing light on the ground can capture this light. They are mostly effective at nighttime. Post-fire mapping helps us understand the extent and the severity of fires, and some of the satellites and sensors for detecting active fires include MODIS, VIIRS, GOES, Landsat, Sentinel-2, Sentinel-1, and you were provided some overview of these briefly in part 1. It is also important to remember that although there are a variety of post-fire impacts that affect our ecosystems, they are a natural part of forest, grasslands, and tundra environments. There are several post-fire impacts, including, but not limited to, impacts on habitats, human lives, and infrastructure. Following a fire, the impacts can also include a release of carbon dioxide and soot particles into the atmosphere, thereby influencing climate, a change in soil chemistry, and a reduction in soil fertility, destruction of vegetation leading to increased runoff and soil erosion, as well as influence on nutrient cycling and flow. And the obvious big one of destruction of ecosystems and wildlife. Often when we think about wildfires, we think about the fire intensity and the burn severity. Fire intensity is the amount of energy or heat released per unit time over an area and can be described by a variety of fire intensity metrics. Traditionally, fire intensity is considered the rate of energy or heat released per unit time, per unit length of the fire front, regardless of its depth. Fires of different intensity tend to look very different and have the ability to burn vegetation and soil to different degrees. Fire intensity is important to keep in mind since it's a major factor in determining the severity of burning. Burn severity is the effect of fire on ecosystem properties and is often defined by the degree of vegetation mortality. Burn severity is a way to measure the degree to which a site has been altered or disrupted by a fire, with severity determined by both fire intensity and residence time. The burn severity is something we can measure via satellite imagery, and it is considered a mappable metric for post-fire assessment. From a remote sensing perspective, we usually assess post-fire landscape impacts with 2 metrics: the burned area to determine the spatial extent and the location of burn scars, and burn severity to determine the relative impact of a fire on the landscape. We'll go over more of this in the following slides, but you can see here an example of burned area and burn severity. With these 2 metrics, we're able to use remote sensing imagery to assess the extent and magnitude of fire impacts over large areas. Optical sensors used in remote sensing give us spectral information to examine vegetation conditions. Here, we have the spectral response curve of vegetation plotted over the electromagnetic spectrum from 0.4 to 2.6 micrometers. In healthy vegetation, there's a relatively high response in the green portion of the spectrum due to chlorophyll pigmentation. There is also a high near-infrared response due to healthy plant cell structure and relatively low responses in the mid-infrared range due to water absorption. So that's why we see healthy vegetation as green. We can use the reflectance properties from the satellite image to identify healthy vegetation versus burned areas. When we compare the healthy vegetation spectral signature to those of burned areas, we notice some differences. You can see this pretty clearly for the spectral signature curves of low, moderate, and high burn severity, where healthy vegetation has this large peak in the near infrared, bare soil, and burned areas have much lower peaks in the near infrared. And in the case of high severity burned areas, there's much less response in the near infrared. You can see that healthy vegetation has low reflectance in the shortwave infrared, but burned areas have high reflectance in those wavelengths. With these spectral characteristics, we can identify burned areas and distinguish it from healthy vegetation. To take advantage of this difference in spectral response between healthy vegetation and burned area, we use the normalized burn ratio, or NBR, to map post-fire conditions. NBR uses remote sensing data at the near infrared and shortwave infrared to map burned areas and ultimately assess burn severity. You can see how this calculation is completed here on the slide. NBR is a unitless value from -1 to 1. A high NBR value, that is closer to 1, indicates healthy vegetation, while a low value, that is closer to -1, indicates recently burned areas and bare ground. NBR is a commonly used metric for identifying areas where vegetation has recently burned due to fire. The images here show pre, during, and post-fire from the Mendocino Complex fire that also burned in California in 2018. NBR is also critical to burn severity estimates. To estimate severity, we compare NBR pre and post-fire using the differenced normalized burn ratio, or DNBR. Here we have a basic run-through of how this works. First, we will calculate the NBR prior to a fire and after a fire. We then take the difference between those two images. Once DNBR is calculated, an analyst will need to threshold the DNBR values into classes of low, moderate, and high burn severity to produce a map that looks like the one on the right, with highest burn severity areas mapped in red here. There are suggested threshold values for burn severity in the literature, and using this approach, we can identify the severity of the fire. Now, on to post-fire mapping in Google Earth Engine. Google Earth Engine developers have focused on creating a really robust GIS platform for processing, analyzing, and displaying satellite data. Therefore, Google Earth Engine has a lot of potential for land monitoring applications. Applications like long-term monitoring of landscape change, computation of relevant indices evaluating parameters like vegetation, soil, snow cover, and time series and change detection analysis of land surface features. There are also functionalities for calculating summary statistics, validation, and accuracy assessment, and visualization and presentation of results. There are also a variety of processed land cover layers available, including the Copernicus Global Land Cover Layers dataset, MODIS land cover types, maps of forest versus non-forest area derived from pulsar data, and the USGS National Land Cover Database layers. Linked here, you can browse the data catalog to get a better idea of available data layers and imagery archives. For part of this training, we will be using Google Earth Engine for burn severity mapping with Landsat data. We will calculate the normalized burn ratio and the differenced normalized burn ratio, utilizing thresholding values to identify categories of burn severity and map them within the interface. Portions of the code we will work through in our exercise are from the United Nations SPIDER program, where they provide an example of burn severity mapping in Chile in 2017. This code is publicly available and flexible to use in different regions throughout the world. The information is linked here. As with any platform, there are advantages and disadvantages of Google Earth Engine. Some benefits include rapid processing of imagery on the cloud, the ability to access and integrate many different data sets. The built-in functions allow for relatively quick processing, and you have a flexible API where applications can be built off Google Earth Engine, like Climate Engine, or the popular Global Forest Watch. It is also free for non-commercial use. Some disadvantages include limitations for some of the processing operations, meaning you often cannot run batch operations without a cost. If you are a commercial user, there is also a cost. Some complex processing can also be challenging due to the restricted programming framework. Additionally, aggregate layers make it difficult to determine the date of specific pixels. I'd also like to take a moment to acknowledge that in addition to land monitoring applications, there are many factors to consider when evaluating environmental, social, and economic impacts of fires. The study by Morton et al. Listed here provides examples of variables that capture a fuller story of post-fire impacts. Although we do not go into depth for many of these listed here, we encourage you to explore ways to augment your own post-fire analysis by incorporating the many ways in which a location is impacted by fire. We are now going to enter a demonstration of Google Earth Engine led by Britnay. Britnay, take it away.
Thank you so much, Sativa. In this session today, as she said, we're continuing with the Woolsey Fire as our case study, and we're going to be using Google Earth Engine to look at some post-fire impacts. So we'll start by using the Landsat 8 Collection 2 dataset, which is linked here above on the slide. And Landsat 8 is great because it has global coverage, it has 30-meter resolution, and has data available from March 2013 to present. So with this data, we'll start by masking out clouds, applying a scale factor, and filtering our data to pre- and post-fire dates. And the image on the right here shows a true color image of our study area. We will then use that filtered Landsat 8 imagery to calculate a normalized burn ratio, also known as an NBR. And we do have this formula for an NBR right here on the top right. And we will use Landsat 8's near infrared and shortwave infrared bands, and we'll calculate the NBR for both before the fire and after. And on the left, we have a screenshot of what that layer will look like, where darker colors indicate healthy vegetation, while the lighter colors indicate bare ground and recently burnt areas. Once we have the pre-fire NBR and the post-fire NBR from the previous slide, we will take the difference between them to calculate the DNBR, also known as the differenced NBR, or the change in the NBR from that fire. So with the DNBR, we will then create classes for the burn severity index, and the thresholds for this burn severity range from enhanced vegetation regrowth to high severity burn. So the thresholds we're using in this code today are based on the J.E. Keeley fire intensity, fire severity, and burn severity, a brief review and suggested usage that the UN Spider tutorial also recommended. This image on the right shows our study area with the burn severity color-coded according to the various thresholds that we just mentioned. The next layer we'll be working with today is the Copernicus Global Land Service land cover data. This data has global coverage and is calculated on an annual basis, but the Google Earth Engine version has not been updated since 2019. The data also has 100-meter resolution, so that's something to keep in mind as well. But since the Woolsey Fire is from 2018, we are going to be using this data set specifically with the 2018 land cover. And the image on the left shows our study area and its various land cover types. And in this session, we'll be focusing on the urban classification and using it to calculate hectares of burned urban area. The next layer we'll be working with is the global human settlement layer, which contains the amount of people per cell for various years. And we use this layer because it has global coverage, but it does have 250-meter resolution. And unfortunately, the closest date to our study area is from 2015. But we will be using this layer to estimate the number of people affected by the Woolsey fire with the burn severity map that we just saw a couple slides ago. Next, we have the VIIRS day-night band. This data is an average monthly composite of radiance, and it has global coverage and is available from April 2012 to present. And its resolution is about 460 meters. However, we will use this data to look at our study area before, during, and after the Woolsey fire. And our next layer is the Fire Information for Resource Management System, also known as the FIRMS dataset. FIRMS distributes near real-time active fire data from the MODIS and VIIRS instrument, and globally these data are available within 3 hours of satellite observation. While FIRMS does have its own website and its own active fires map, it's also available as a layer within Google Earth Engine. So we're going to add that to our map and further examine the extent and the severity of the Woolsey fire. Okay, so at this point, we're going to use the link here at the bottom of this slide in the blue to open the code in our Google Earth Engine code editor. And we're going to go through the code one section at a time to further understand the layers we just discussed. And here are the 9 sections we're going to get through. And with that being said, let's go over to the code editor. All right, so now we'll examine some Earth Engine code and discuss how we created the layers we just went over in the presentation. Since this is an advanced level webinar and session 1 already covered several aspects of Earth Engine, as we go through the code today, we're going to approach it from the perspective that we have at least a baseline understanding of the coding language. So if you want to learn more about Google Earth Engine and how it works, I suggest you review the webinars listed as prerequisites for this series, as well as these other webinars and tutorials we have listed here at the top. So sections of this script were adapted from previous ARSET lessons and UN Spider tutorials, so we've provided links to those as well if you'd like to see that more in depth. All right, so with all that being said, I think we're ready to dive in. Here at the top or the start of the script, we do have just some more layers and information to continue from session 1. So the first thing that we have starting here at line 17 is creating a title for the map window. That was in session 1 for both of the scripts that we used, and we're doing the same thing here. So, we're just creating the variable title, and on lines 19, we're just, adding that text here to this, and then we're just picking the font weight and the font size and its position, and then we add it to our map here on line 25. And then again, just similar to session 1, we're adding the hydrosheds basins layers, including level 9 and level 7. So here we start on line 29 with level 9. We just create a variable with that data set. Here on line 31, we just create the visualization, picking the color for it, a nice blue. And then we add that visualization to our map here. And then we do the same thing for level 7, starting on line 41, picking the visualizations, and then adding that to our map. So here in Earth Engine, as you add layers to your map, and it starts from the bottom all the way up. So as we go through the different layers today, we will be starting from the bottom and working our way to the top of these layers. So let's start with layer 9, and here's our watershed of interest that we were looking at in previous sessions for this fire. And then we also have layer 7, and it's a bit of a larger scale, so you can see how that changes as well. For the most part, as we add most layers, I'm going to be referring back to level 9 here and seeing what it looks like within our specific watershed, but this is something just to pay attention to. All right, So jumping into part 1 of our new code, we're going to define our study area, we're going to apply a scale factor, and we're going to cloud mask our data. So we're starting with defining our study area here on line 56. On line 57, we're just creating a variable that we named ROI, and ROI is our geometry here. It's this nice sort of square rectangle area that covers the extent of the Woolsey fire. So that's our region of interest. I'm going to turn it off just so we can see our watershed, but that is our geometry that we'll be using today. And from here, we just set the background to be a satellite imagery, just so we can better see what this watershed looks like. You can always switch to map here down below if you'd rather, look at, like a street view level. But I like the satellite better for some visualizations today. And then we're just setting the map center to better visualize what we're looking at each time we run the code. Okay, so here on line 62, we're setting the pre-fire dates. So on line 63, we have the pre-fire start date and the pre-fire end date on the next line. And as you can see, we go from November 5th, 2017 to 2018. So we're doing about a full year before the fire. That's so we can just get a full understanding of this region, its seasonality, just trying to encompass as much as we can with the imagery. And then here on line 66, we're having the same parameters for after the fire. These are the post-fire dates. So on line 67, we have the post-fire start date, and that's just the day after the fire officially ended, and the post-fire end date, and that's about 3 months after. And that's something to think about too with your post-fire start date and end date. The length of your post-fire date, you have to think about, clouds and the quality of the imagery that you're getting. But also if you extend too far, what areas are starting to grow back vegetation? How does that affect your results? So we have about 3 months here, but as you do your own research and as you play with this code on your own, start to think about how changing those post-fire dates might change some of the results you see below. All right, so here on line 70, we are applying a scaling factor for the Landsat 8 collection 2 image collection that we're working with. And I have included a link here if you're just interested in scaling factors, but essentially this is just going to help us scale down the values within the data so that way they're a little bit more easier to manage with visualizations and things like that. So we are just performing this scale factor here on the optical bands and then this scale factor here on the thermal bands. And again, you can read more about that in the link provided on line 70 if you're interested. Okay, so here, starting on line 78, we're starting to pull in these image collections of our pre-fire dates. So we have on line 80, we're creating this variable pre-fire image collection, pre-fire IMCOL. And we were pulling it in, and then we're filtering by the dates. Again, our pre-fire start date, our pre-fire end date, that full year before the fire began. We're filtering by our bounds, which is the region of interest, this geometry, our ROI, and then we're mapping these or applying the scale factor that we calculated above. And then we're doing the same thing for our post-fire image collection. We're creating this with the variable post-fire image collection. We're filtering by the post-fire start date and the post-fire end date. We're filtering by this geometry here, and then we're applying that scale factor. All right, so here starting on line 95, we're starting to cloud mask the data, or at least we're creating a function that will be performed to cloud mask the data. Here I'm just masking out a couple different types of clouds, cloud shadows, and I'm also masking out water, which may sound interesting. And we're doing that because a lot of the different calculations that we're going to be doing today are specific to land. And as you can see, our geometry here does cover a bit of the ocean, and I don't want that included in our calculations if we can help it. So if you are performing this at a later date over a different study area and you don't want to mask out water for whatever reason, you can always get rid of line 102 and 110 here, and you should be able to just mask out clouds without masking out water. but just for that reason, you will see that I am attempting to mask out the water, and once we add it to our map, you can see it does, for the most part, mask out water. But this is just the cloud mask function. And then here on line 117 and 118, just because we created that function doesn't mean we applied it yet. So we are applying that cloud mask function here. So on line 117, we're applying this cloud mask function using the map feature here on the pre-fire image collection and the post-fire image collection. So these new variables are called pre-fire CM cloud mask image collection and post-fire CM for the cloud mask image collection. And then here, starting on line 20, we are mosaicing and clipping the image to our study area. So we are taking a mosaic of all of these photos in our image collection and clipping it to our region of interest, meaning we're like taking a cookie cutter and just cutting out this specific area for our image to add to our map. And we're doing that here on line 124 and 125 with the pre and post fire image collections without the cloud mask. And then on lines 127 and 128, we are adding the cloud masked versions of the image collections as well, just so we can see how the cloud mask and the water mask function works on our image collection. So here on line 131, we are creating some visualization parameters. We're just picking bands 4, 3, and 2, our true color imagery for our image collections. And then here, 134 through 139, we are adding these different layers to our map. So we have the pre-fire image collection, the post-fire image collection, and then the true color versions with the clouds masked as well. So let's look at that now. So we're going to the Layers tab, scrolling to the bottom here. And as you can see, we're going to start with the pre-fire image. And as you can see, it's still loading a bit. Okay, so it does have some streaks from clouds within the imagery. So from there, we're also going to use, or we're going to load the cloud masked version. Okay, so here it definitely got rid of that big streak of clouds, but we do have some down here. And you know, it's not perfect. I think it's good enough for our analysis today, just to get rid of all of that ocean we had. If you wanted to make it absolutely perfect for this study area, I think that we could always use like a shape file without the ocean included. But for our purposes today, I think this is all right. And then we're just going to view the post-fire image. And here we have some clouds as well. And then the post-fire with the clouds masked. All right, and you can see there's a little bit emptiness here, but again, that's okay. And you know, if we wanted to increase our post-fire dates, that might help fill in some more, but then you have to think about how long it's been since the fire itself and the results. So this is all a fun puzzle that you have to work around as you work with remote sensing imagery. But the good part is that, as you can see, that water from down below has been masked out. Okay, so let's move on to part 2, calculating a NBR for our pre and post fire images. So here is the calculation for an NBR, and we're going to be doing that for both before and after the fire. So we have a pre-NBR, and we are using Landsat 8's near infrared and shortwave infrared 2 bands, and that is band 5 and band 7. If you're doing this yourself at a later date and you're using a different satellite or a different sensor, make sure that you are using the near infrared and shortwave infrared bands and not just bands 5 and 7. Make sure that you are using the correct ones there. So we are using, again, pre-NBR, post-fire NBR, and using the normalized difference with these bands. Which brings us to part 3. What are we doing with them other than just creating them? We are creating a DNBR. We're using them for a DNBR calculation where we subtract the post-fire NBR from the pre-fire NBR. And we do that right on line 156 with the variable dNBR unscaled. So again, we're just subtracting the post-NBR from the pre-NBR. And then we are scaling it to USGS standards. So what does that mean? The NBR, again, is on a scale from -1 to 1, but we are multiplying it by 1,000 here. So that way, when we work on our burn severity, we have these larger numbers to work with, and you'll see why as we get to the next section of our code as we're working with our thresholds. But we're just multiplying the results by 1,000 for just our dNBR. And then we're adding the pre-NBR, the post-NBR, and the dNBR to our map here on line 163, 164, and 165. We are just using this, gray palette to do so. And we can check that out on our map now. So I'm going to the Layers tab, and let's start with the pre-fire normalized burn ratio. So this is before the fire. And then we can compare it to after the fire. And right away, you can see a big change, especially if you turn these layers on and off or make one, see-through. You can see, this lighter colors here showing this burn scar in the area, right? And then this regrowth here, this darker area, a couple months after the fire. And you can also add the dNBR grayscale, so things are switched here, but you can still see that burn scar and whatnot. So we're going to be using this dNBR to calculate our burn severity, and we're going to sort of, attach the legends and color code it to make this really cool visualization of the burn severity. And we're doing that next here in part 4. So we're going to classify the burn severity, add a legend, and identify where in our map is a burned area. So what we're doing here, starting on line 172, is we're creating these thresholds, these different intervals of values of data that we're going to use for the severity of the burns in our data. So we start with like -1,000 all the way to -250, from -250 to -100, from -100 to 100, so on and so forth. And from there, we're adding that to our map, and we are going to create these thresholds again here on line 190, 191. We're creating these thresholds that we're going to do for our 8 burn severity classes. And then from here, we are creating a legend for the classification. This code is exactly from Google Earth Engine's tutorial on how to create legends. We're just creating it for our classes and changing the values. It's straight from the UN Spider tutorial as well. So as you can see here, we are just creating the legend title. We're adding the title as a panel. We're changing the colors, the fonts, the size of the fonts. Here we're picking the palette for each of our thresholds, classes, and then naming each of them. So these are just color codes, and you'll see those in a second. And then we're just, creating it and then printing it. So here on line 251 and 252, I have selected to run this line here, 252, to print our legend here to the console. But if you'd prefer, you can also just mask out. You can comment out our line 252, and you can run 251 instead. And I'll do that just to show you why. And it'll add it down here. But we will be working with more legends today. We're going to be working with more colors, and I didn't want the legends or permanently in the corner here because I thought it would be distracting if we're not looking at this specific map the whole time. So that's why I have it just as a printed version instead of as the map. But again, this is up to your preference. I like it here printed to the console instead, so I can always scroll to it, but it's not always in the corner. So now that we have our legend, let's add that layer to our map, and that is under dNBR classified. So here we can see all the classifications, the enhanced regrowth in this area, the high severity burn, the low severity, the different versions all right here and up here. And I will draw this to your attention very quickly. Something like this, and it even shows up in our grayscale as well as our burn ratio. This here are not just very localized high severity burns. This is actually just changes in agriculture. So this is why it's so important to, when you're doing with, or when you're working with remote sensing data and doing these calculations, you have to make sure that you know the area well, because this is not just a very localized burn. This is probably like a form of crop rotation or just a change in the agriculture. There was a burn here within this area itself, but it was not a high severity burn just within these couple fields here. So that is something to think about in your calculations. You could either crop that out or remove it, but it's something to think about. But looking at our Woolsey fire here, I will zoom in and turn on the hydro sheds level 9, and I'll start to see, so you can see the high severity burn was right here at the bottom, almost along the edge of our watershed of interest, and even the watershed beneath it, you can see how severe that burn was right along that line there, that ridge. So that's something very interesting to think about. And then you can see the burn was through here as well, and this area has experienced regrowth by the time our post-fire dates have occurred, but the fire did go up here as well. And you can even see the burn scar in a previous slide within our presentation. I believe it's Modus imagery where we got that. Yeah. So now that we have this burn severity map, in this next section, starting on line 254, we are identifying the burned areas specifically, and we're going to do that by just working with the low severity to high severity thresholds. So here in the console, we're working with anything from low severity to high severity, burns in this area. And we're doing that on line 255 by creating this burned thresholds, and we're working with our DNBR, and we're just getting all the values greater than this .GT 100. So 100 is the lower area for low severity, so we're doing everything greater than that for our burn severity in our map. So, and from there, we're creating another variable on line 256 called burned areas, and we're updating that mask. So we're masking out anything that was not within our burned thresholds area. So we're just creating a map or a layer specifically to look at anything that is classified as burned. And so we're going to create these visual parameters for the burned land, just picking a color palette to separate it from these other classes as we add it to our map. I believe this is a nice like navy blue color. And so here on line 264, we're adding that burned area to our map. So let's add that now. And that's burned area here. And on top, you can see this burned area is this navy blue. We can even turn off the lower area now. And so this is our sort of extent of the Woolsey fire based on these classes in our burn severity. So we're going to be working with that in a bit. So we're moving on to part 5, add land cover data and calculate hectares of burned urban area. So we're going to start by creating a variable for the Copernicus Global Land Service land cover data. So on line 272, we're working with the variable LC_global. We're just adding this Copernicus land cover data, and we're selecting the discrete classification band. So I'm just going to add, just going to show you really quick what this data set looks like. So if I open this here in a new tab, so this is just, right from the Google Earth Engine data catalog, information about what we're working with. But we are working with the discrete classification bands. This is all the different land cover classes. So here are all the different ones that this data set offers as land cover classes. here in the Woolsey fire and just in our area of interest, we only have about 7 classes, so only about 7 of these show up. So we're going to use those 7 to create a legend next in our code. And we did that just by taking this exact color code and this exact title as we create the legend title and the different classes. But as you're working on your own and you want to create a legend, or if you are using this code and you don't see these different colors showing up in your legend, you're going to have to edit the color codes and the titles yourself. I just wanted to make that clear. Okay, so the first thing that we did, again, is just selecting that discrete classification band. We're clipping it to our region of interest, and we're adding it to our map as land cover. So let me add that now. And here you can see our land cover, and I'll turn off that lower area, and you can see the different land cover types within our watershed of interest. You can see a couple different kinds, and we can explore that once we add the legend. Okay, which is the next section. So this, again, this legend code is very similar to the previous legend code for these classes that we just added. Just adding the position, giving it a title, picking the font weight, the margins, all of that information, how the text will flow. And then again with the palette, these palette colors and the names for each of the areas in the palette, that's just coming right from here. The ones that we saw down here below to create our legend. So again, we just saw 7, so we just have 7 different classes within our legend, and we add that. Again, same scenario with the map and the print on line 335. You can add it by mapping it or adding it to your map down below if you want to run line 335. I ran line 336 because I just want to look at it right here in the console. And so it printed right here, and we have our land cover classes. As you can see, this orange color is shrub, yellow is herbaceous vegetation, red's urban. You can see that in our area of interest. And so this can also be a good way to look at your, burn severity map, look at your, different values, like this is agriculture, maybe this wasn't as increased of a burn as I thought, and this is like a misclassification in my DNVR. Something to think about. Okay. So what we're going to do next is display the urban areas as a separate layer on the map. So we're going to take these red values here, we're going to separate it and make it a brand new layer because we just want the urban layer as something to work with. So the first thing that we do is set some visual parameters, and we're just picking a color for these urban values. I believe this is a purple color that we're going to add to our map. And we are extracting these urban values from the land cover on line 346 using LC, that land cover dot equals 50. Where did that value come from? It came from right here within the discrete classification here. The value of 50 is the urban built up land that you see down here below. So we just want everything that equals that. And then we create a new variable, and it's called urban, and we're just updating that mask, just updating our selection of values to only include that urban. And then we add it to our layer here, add it to our map as a layer here on line 357. And that's just called urban. And you can see it is a separate layer. I can even turn off the one below. And now this is all of the urban area within our complete region of interest. You can see it over our watershed here. Okay, and here we're going to calculate hectares of burned urban area. And how we're going to do that is we're going to use this data, this urban classification, along with the burned area classification. So by understanding where the urban area is and where the burned area is, we want to see where they overlap. We want to see where there is an urban area that was burned by this fire. And so that's what we're doing exactly on this line here, 362, var urban affected. it equals the burned areas. Again, this blue color here, using that dot update mask, changing the visualization, what we're selecting for data, and we only want to look at it where there's also an urban value as well. And so from there, we're just adding that to our map right here on line 366. We're adding that urban affected map using some visualizations. I believe it's a bright pink color that I think is right here on line 351. And so we're adding that, and I believe it's called burned urban. And so I'll turn these other off because you can see it a bit better. These are all of the burned urban land from the fire here within our map. You can see all of it. And then within our watershed here down below. Okay, so we want to get an understanding of how many hectares. So we're going to start by getting the pixel area of this affected urban layer. So what we're going to do is we are going to add a pixel area here just to calculate the area of each pixel within this data set. And then from there, we are going to sum them. We're going to take the sum of them, and we're going to do that within our entire region of interest. And what's important is when we are counting all of the pixels, we have to set the scale, and it's important that the scale is the same as the data set that you are getting your data from. So as we're counting all of these different pixels, we need to make sure that the size of the pixel, the scale, is the same as our urban layer, which comes from the land cover data set. So we know that the resolution for our land cover data set is 100 meters, so our scale is 100 here as well. And then here we are just going from meters to hectares as we summarize or get the sum of our pixel count. And then we are just rounding it to the nearest whole number. And then we're printing that number again to our console and adding just a title of hectares of affected urban area. As you can see, our value here is about 4,268 hectares. All right, so for part 6, we are going to load human population data and estimate the number of people affected. So we're going to start by loading the JRC, Human Global Settlement Population Density layer. So we're going to start with line 395, just adding that JRC data and of course clipping it to our region of interest. Again, this is 2015 is the closest year. So we're working with this 2015 data, and then from there, we are creating a raster, just showing the exposed population only using the burned areas. So now that we have the entire information on the population within our region of interest, we want to look at how many people were specifically within this area that, let me turn off all the layers except for the burned area. So now we're looking at the count of the population that were specifically within this burned area who were most directly impacted by this fire. So we are just updating the mask so that this is the only area that we're going to be counting our population value in. And we start that here on line 401. We create a variable on line 402 called stats, and we're just again taking that exposed population, using the reduced region, taking the sum of these pixels, and again, scale comes up again. It's important that the scale matches the scale of the data set that you're working with. So it's a 250 meter resolution, so that has to match. So we're making sure that our scale is 250 for this one. And then here on line 410, we are just getting that number and then rounding it to the nearest whole number. And then we are printing that here on line 412, which is 14,723 people affected. All right, so with these socioeconomic calculations, we need to remember that our results are only as accurate as our data, and these values are only meant to give us a broad idea of the scale of hectares burned and the scale of people affected. So with these calculations and with remote sensing data in general, we need to think about how both the spatial and the temporal resolution of our data affects our results. So we chose this land cover data set and this human population data set because they provide several years of global coverage, but I would encourage you all to consider what other data sets are available within your own study areas and consider what their spatial resolution looks like, what the temporal resolution looks like, and how an improved version may improve your results as well. All right, so on to part 7. We are going to visualize nighttime data before, during, and after the fire. So we're using that VIIRS day and night band data set, and we start with the pre-fire here on line 418. And we start with just selecting the data set, selecting the average radiance band, and then again, this is composited monthly, so we're just taking all of October 2018 as the month before the fire, and that's our pre-fire. And again, we're just mosaiking and clipping it to this geometry or region of interest. And then we're doing the exact same thing on line 425, and then again on 432 during the fire, the entirety of November 2018. So this is just a complete month. So it does last before and after the fire occurred. So it's not the exact fire dates. And then the post-fire is the entirety of December 2018. And then here, line 440, 441, and 442, we add them to our map as nighttime before fire, nighttime during fire, and nighttime after fire. You can see that here. So here's the before. Again, the resolution's a little coarse, especially as small as our region of interest is, but it does offer some really interesting understanding of our area. So even just looking at this, we can see a lot of these lights are coming from urban areas in our region of interest at night before the fire. And then of course, during the fire, we have a lot brighter areas which don't look or they don't seem like they're urban areas. So we can compare that to something like our burned area, and we can see which areas were burning at this time when this image was taken. And then of course we have the nighttime imagery after the fire, and we can, compare all three and just see how things change before, during, and after. And the difference here, before and after, isn't that extreme, but it may be in other areas. And it's just another interesting way to see the extent of the fire, how things changed, socially. It's definitely a very interesting perspective here. Okay. And then, here on part 8, we are visualizing firms data during active fire dates. So on line 449, we're taking the variable firms, we're selecting the active fires band, and then we are adding the exact dates of the Woolsey fire, and of course, filtering our bounds to our region of interest. We're mosaiking and clipping it, setting some variables for the visualization here on line 456, and picking a color palette, and then just adding it to our map on line 461. So let's see what that looks like. And again, the resolution on this data, I believe, is about 1 kilometer. So it's pretty coarse, but it's still interesting just to compare the extent of the fire as well as the severity. Just another way to look at our data set from a new perspective. All right, and then our last part here, part 9, visualize pre and post-fire NDVI. Of course, session 1 had that really interesting NDVI anomaly section, so we just thought it would be interesting if we had some NDVIs before and after the fire to look at as well. So here on line 467, it's just the calculation for NDVI. So we're using the near infrared and the red bands in Landsat 8, which are bands 5 and 4, and we're doing that pre-fire, and that's line 468, and 469 is the post-fire NDVI. On line 471, we're creating those visual parameters, the min and max values, -1 to 1, white and green for the colors, and then we're adding both to our map as our final 2 layers all the way up here at the top, pre-fire NDVI and post-fire NDVI. And then here's just the end of the script and our disclaimer. So let's look at our last two layers. So here's before the NDVI and after. And you can definitely see, if we zoom in here, and look at our watershed, of course, our watershed of interest. And you can even see that burn scar and these changes in the vegetation before and after. I think it's very cool. All right, so this is the end of our code today. So we are going back to the PowerPoint now, where Sativa will give us some information about NOAA's hazard mapping system. Feel free to take it away there, Sativa.
Okay, thank you, Britnay, for that demonstration. For this portion of the training, I'll briefly walk us through NOAA's hazard mapping system, or HMS Smoke Explorer, which also has been made available as a Google Earth Engine application. The link to the NOAA site is here on this slide. So this smoke product maps the extent of fire-related smoke plumes across the United States and adjacent areas. When you enter the NOAA site, there are a variety of resources related to this product, such as maps, data statistics, more about product information, and other useful links. According to the website, the hazard mapping system was first implemented in 2003 in response to high demand for active fire and smoke information over North America. The HMS outputs included active fire detection and smoke information for a 24-hour period. The system combines near real-time polar and geostationary satellite observations, and currently the HMS uses the 2-kilometer resolution data from geostationary satellites GOES 16 east and GOES 17 west, 375-meter resolution VIIRS data, and NOAA 20 polar satellites, as well as the 1-kilometer resolution MODIS data from the Terra polar satellite. Complementary USGS Landsat 7, Landsat 8, ESA Sentinel-2 data are also used to support daily fire analyses. You can find details about the data under product information. HMS's fire detection information is published online using the HMS data mapping interface and made available in GIS-friendly formats such as KML and shapefiles. The website provides the most recent HMS analysis, and so feel free to explore the interface for yourself by adjusting the date of interest and getting more information on the layers available. So here is just an example of that interface on the NOAA website itself. And you can click here to adjust the parameters. So I'm going to hop back on to the PowerPoint for a second, because we are actually going to return to a Google Earth Engine app version of the HMS system and walk through a short demonstration focusing on the Woolsey fire. Okay, so here we have the HMS Smoke Explorer as an Earth Engine app. We have a couple of links here at the very top. Data and info will take you back to that page we were just on from NOAA itself. And then there's also a link here to the code that you can choose to incorporate in your own analyses in the future. So just wanted to give credit where it's due and show where that product was developed. So we are able to use this user-friendly tool and adjust for 4 input parameters. We have the view mode, which allows us to go by day, by year, or a summary. We have our select year, select date sections, as well as the satellite. And in order to look more closely at the Woolsey fire, we're going to adjust our date. We're going to keep it by day. We're going to go to 2018. And we're going to go to November 9th of that year. We're also going to adjust our satellite to GOES West and select Run. The analysis will populate, and you can scroll down to view the legend here on the left. You can see the extent and density of smoke plumes observed from the satellite images, and the NOAA's HMS analysts spatially aggregate this data by smoke density categories. So if we scroll down, you'll see right now we're displaying for smoke. You can select that on and off, able to change the transparency there. We also have active fires, which are detected by MODIS and displayed by red dots on the map. Again, you can click on and off for those. You can also add in aerosol optical depth as a layer. So we have either for MODIS, Terra / Aqua, we have data for the multi-angle implementation of atmospheric correction product. That's the NAIAC right here. As well as the Copernicus Atmosphere Monitoring Service from the European Center for Medium Range Weather Forecast. And this is at 550 nanometers. CAMS right here. Switch between the two. Okay, so there's also surface particulate matter 2.5 available from the same provider with daily average particulate matter concentrations in micrograms per meter cubed. And you could find this data on the Google Earth Engine data catalog. Lastly, there is a time series chart produced of smoke plumes for the year of interest. You can filter by density category and also download. Okay, and you're also able to get more information under the smoke text description, where you get a descriptive text narrative for smoke and dust observed in the satellite imagery. So it has more about the narrative there. Let's see. Great. All right, so you can zoom in closer to where the Woolsey fire was taking place. And I find it helpful to zoom in and out regularly to connect the specific area of interest to regional trends. And as you notice, there's another fire occurring during the same time period. And I just kind of want to show, if you click through dates, excuse me, can rerun the analysis and observe the differences and trends over time. You can also plot the GOES 17 West RGB images on this map, but this is only possible for days after December 4th, 2018. So right now, we are unable to do that, but if we are looking at a different fire with times after that period, we can adjust. And, there's different ways to sort of observe the map to, get a look that is most helpful and useful for you. All right, so that's just a quick overview, and we're going to pass it back to Britnay to close out our session. Thank you.
Thank you, Sativa, and thank you to everyone here who attended this session and all the other sessions throughout this past week. We're going to wrap up this session really quick with a summary, some resources, and contact information before we begin the Q&A portion. So to summarize this final session 3 today, we learned about monitoring changes in NBR and DNBR and how they can help identify the extent and the severity of wildfires. we learned about land cover types and human population data and how that can be used to estimate the affected population from a natural hazard. And then we learned about data sources such as the Beers Day-Night Band. We learned about firms and even more, and how they can be used to further understand fire extent and the affected population within a study area. And now to summarize the complete training for assessing the impacts of fires on watershed health. In sessions 1 and session 3 today, we used Google Earth Engine, and we learned that it can be used to delineate river basins and subbasins for a watershed of interest. We learned to calculate anomalies in biophysical and meteorological conditions. And we even learned to map burn severity and data sets relevant to post-fire impacts on landscapes and populations. And of course, in session 2, we learned that SWOT can be used to develop a river basin scale model and to quantitatively constrain fire-related increases in water quantity and quality parameters. So this slide here is just a reminder about the homework and the certificate of completion. We have one homework assignment for this webinar. It opens today, here the 13th, and you can access it from our training webpage. As a reminder, the answers must be submitted via the Google form. That is that link on the training webpage, and that's due 2 weeks from today on July 27th. In order to receive that certificate of completion, you must have attended all 3 live webinars, which was recorded automatically when you joined, and you must complete the homework assignment by the deadline, which again is just 2 weeks from today. And you will receive a certificate via email about 2 months after the completion of the course. Our production team here works very hard to get through all of the homework and all of the attendance, so please be patient as they sort all of that out before you receive it in your inbox. And lastly, we have just a couple people that we wanted to thank. Our team here at the Ecological Conservation team, of course, our Water and Disasters team, and our guest speakers from session 2. And here is all of our contact information. If you have further questions, you can contact myself or my ARSET colleagues at our email addresses. And as a reminder, here's the course website where you can find all of the information regarding the PowerPoint, the homework, and other tutorials that you might be interested in as well. And then we have just a few resources related to the subjects that we talked about in this session today. So I highly encourage you to use them to learn more about these topics and explore a bit deeper. Thank you again. And at this time, we will begin the question and answer portion of our session.
Right, so throughout the training today, we have been compiling the questions that were added to the questions tab, and we've been attempting to answer them here. And we're joined today by our various organizers for this training series, and we've been trying to answer them as they come in. So we'll go through some questions now, but if we don't get through all of the questions we have here today, we're also going to post this Q&A document on the training website in a few days. So you can always check back and look at some answers there later. So with that being said, we can jump into question 1. Has anyone examined the progress of a fire as an event progresses over time with the goal of predicting where a fire will move next? Clearly, wind, if present, will be a factor, but topography, fuel, and other factors are also important. To answer your question, yes, there are many different programs out there and researchers studying how various parameters affect fire spread. And we've linked a couple that are some NASA-supported programs that we definitely encourage you to look at, but that is definitely a very interesting and exciting field of fire research that's very active that you can definitely look into and do some research on. All right, so question 2. Do we have a script to calculate SPI in GEE? Yes, so session 1 of this training explains what a standard precipitation index is and how to create your own in Google Earth Engine. And you can access all of the session 1 materials and information right on the training website. And then you can access the code from that training as well. And the SPI information starts at about on line 71 in that code. So feel free to check that out. All right, so for question 3, what is an RDNBR? And that is a great question. So a RDNBR is a relative difference to normalized burn ratio. And I have a quick definition that I got online from the, let me check, the Monitoring Trends in Burn Severity website. And we didn't calculate that today, but it's a normalized version of the DNBR that we did calculate. So it's sort of removing that biasing effect. So in our DNBR that we calculated today, that was just pre-fire NBR subtracting the post-fire NBR. And the algorithm for an RDNBR is right here. And so I have a source to that original website I just mentioned, as well as the actual publication that discusses using an RDNBR in fire research. So definitely check those out as well. Okay. Moving on to question 4. If we mask out the cloudy pixels and replace them with other pixels, doesn't it affect the accuracy of the work? And in a way, yeah, it can, definitely. It depends on the amount of time that you're using for your start and end dates for your imagery. I think that's going to make the biggest impact. So if you look at our pre-fire imagery, those start and end dates at the top of the code for section 3, you see that the dates are a full year before that fire. And you can see in those cloud-free images when you bring that first layer up on the map that there aren't any missing pixels because we have all of that data, right? All of those images over that full course of the year. But then if you look at our post-fire imagery, we're only using about 3 months after the Woolsey fire ended, and you can see in those layers that there aren't any, there are a couple of places that weren't cloud-free, and those pixels are empty. You can see right through them to the base map. And if we wanted pixels over the entire study area, we could, expand those start and end dates, but then we'd be moving further and further from when the actual Woolsey fire started, right? And that would start to affect things like, how the vegetation was burnt, the burn severity, and, moving further and further, even if some of the vegetation's growing back, things like that. So that would alter, on an individual pixel basis, what the actual date of that imagery in the data is. Would any of our other panelists like to add anything before I move on to the next question? Okay, maybe not. All right, so moving on to question 5. If a fire occurred in an area of frequent cloud coverage, is there a way of doing post-fire analysis using SAR instead? Definitely, there are several articles and publications and research online that uses SAR for fire analysis. I also included some links to a previous ARSET training that discussed using SAR for forest monitoring, as well as another ARSET training that discussed using Earth observations for pre and post-fire monitoring. And in that lesson, we don't use SAR directly, but it is discussed and it provides links to it in Google Earth Engine. So feel free to check all of those out and get started. All right, question 6. Are the burn severity classification classes defined in literature, or do you have to adjust them to the individual fire? So there's a lot of literature that discusses burn severity classes and how to best define them. That's a really big topic. So for this session, we followed a specific publication done by USGS, and it was recommended also in the UN Spider burn severity mapping lesson that we mentioned. And so the link to that publication itself is actually in the slides, I think on the burn severity slide. So you can read that there. And, there are a bunch of different ways people feel that there are good ways to monitor burn severity and define the thresholds for the severities themselves. And the Monitoring Trends in Burn Severity program does a really great job of reviewing all of those, as well as explaining their own methods. So I included a link to that as well. Would any of our other panelists like to add anything to this question? Okay, so moving on to question 7. How can we calculate the actual burnt area that we illustrate on the map? For example, a percent earned, percent area burnt moderately, a percent burnt area completely, and so on. And we, great news, we performed that calculation in Google Earth Engine during part 2 of a previous ARSET lesson. It's the using Earth observations for pre and post fire monitoring training. And you can look at the materials and the code that we do that there, linked right below. So definitely check that out. I believe you're even able to export it and whatnot, so you can get that code there. Okay, question 8. Is there a method for assigning an uncertainty value for the hectares of affected urban area? That's a great question. I don't know that off the top of my head, as it is from a previous ARSET tutorial that was estimating the amount for another sort of parameter. So I would have to get back to you on that. But these estimations themselves are very, they're very rough, you know, sort of a rough estimation rather than a sure sort of estimation itself. It's more of a guiding answer, but that is something that I can get back to you about unless anyone else has anything they'd like to add or comment. Okay, well then for now we can move on to question 9. When choosing pre and post fire periods, is it important to include the same seasons? Definitely. If you see the pre-fire imagery, that was a full year, and we did that to cover the full spectrum of seasons in our study area before we did that post-fire analysis as well. So, is there anything anyone would like to add to that one before we move on? Okay, so this question here, question 10, relates to the first training. So I believe that means part 1. Given that no gamma distribution was applied to the SPI from training 1, to what extent can it be used to estimate fire risk? If we were going to do a write-up about it, how do we justify using it without the gamma distribution? Would anyone from session 1 organizers like to answer that one? All right, it looks like we'll have to get back to you about that one, and you'll be able to find the answer in the Q&A document in a couple days when it's posted. But for now, we can go to our last question. Is it possible to predict fire locations based on the historical bird scars from 10 years or less? I think that probably depends on the source of the fire itself. So I don't really know the science behind that as well. So that is another question that we'll have to get back to you on, but a very interesting one. But that is our last question for today. But please keep in mind that we will post the full Q&A document for the session on our training website. So be sure to keep an eye out for that so you can read all the answers then. So with that being said, this marks the end of the Assessing the Impacts of Fires on Watershed Health training series. And going forward, you can find all the lesson materials and the homework on the training webpage. So feel free to get started on that. And thank you all again for being a part of this session. Thank you to all of our organizers and our production team And of course, I hope you all have a very great day. Thanks.